representation. This study presents an autonomous charging robot ACR with a master-slave architecture for intelligent automatic charging. The master unit combines a manipulator and the autonomous mobile robot ANR, while the slave unit houses a battery pack and a charger as a function like location, mapping, navigation, and obstacle avoidance are implemented on the robot operating system, ROS. Additionally, integration of Open Charging Point Protocol (OCPP) enable impatient charging information exchange. Experimental results validate the ACR's effectiveness in automatic charging service. In recent times, EV has garnered significant interest propelled by rapid technological advancement and heightened global emphasis on environmental awareness. As the number of EV on the road increases, the issue of insufficient charging infrastructure has become more prominent. Traditional charging stations have best design with each parking space have charging. However, the leads to change like high costs and capital complications. The local of state study to design an ACR to replace the existing charging piles. Currently, the latest models of ACR, like Hyundai Glove's ACR, adopt an all-in-one design where a signal robot handles all functions. However, this design does not efficiently address the issue of insufficient charging stations. The master-slave architecture in this study uses a detachable power source for EV charging. Unlike an integrated design, the expensive manipulator and the ANR don't have to wait during charging. Only a battery remains. The optimizer's ACR results allowing fewer robots to handle more charging demand, requiring only additional batteries. To make the ACR more closely aligned with practical application, this study has designed a system with 5 main components: load, EV, and master, slave, server, and a client. Illustrated in the diagram below. The master unit comprises an ANR, manipulate a camera, and a Udo. Initially, the server dispatches a text message to Udo. Udo then text charge, guiding the ANR to the designated position. Once in position, it activates the camera to obtain the target coordinate through the outcome. These coordinates are then utilized governs the behavior of the manipulator, and enabling actions such as lighting and inserting the charging gun for the charging process. This is master unit space function sheet. The slider unit is conceptualized around a flexible mobile power source. It consists of four main components: charging information exchange and transition platform. The Raspberry Pi responsible for receiving and processing various power control platform, DC to DC converter, Apple button down. Tasked with regulating the charging power. CCS2 charging protocol module manages the charging handshock process. Power supply platform, service battery, provide the necessary power. This is level unit space function sheet. Server integrate messenger between various devices and enable seamless operation through communication. Can handle user charging request. User can simply utilize the SCR through their smartphone. Look, include a CCS2 protocol module which conduct a handshock with the level unit through this module and transmit the charging state to the level unit to ensure the safety of the charging process. The current control in this study is modeled using Physics software as shown in the diagram below. The architecture primarily include upon the voltage mode control method by incorporating an inductor current feedback circuit. This includes both a full feedback current signal and out arrow voltage signal of the voltage loop as input to the PWM modulator, achieving the goal of control both voltage and current. This study employs the circuit configuration depicted in the figure below to implement control pilot CP control. When the level unit receiving a charging task S-link is normally closed, allowing the service battery to energize switch R1. At this point, the charging gun has not yet been inserted into the charging socket, meaning the circuit behind resistor R1 is open. Therefore, measure point 1 will reach service indicating that the charging gun is not yet connected to the charging socket. Upon completion of the connection, machine point 1 will detect a voltage divider consisting of a resistor R2 and R3 parallel with resistor R1. Changes in resistance value will lead to voltage variation at the detection point. The study and concepts for defined state as depicted in Figure 1. Each associated with distinct voltage range as illustrated in Figure 2. Due to the sequential nature of the state and to mitigate potential errors in state interpretation stemming from measurement, this study incorporates a state machine shown in Figure 1 below. The diagram below illustrates the implementation circuit for the CCS2 protocol. In this study, relay server as switches. We utilize the change in resistance caused by the connection of the charging gun. The wires state are toggled through relay control. In this study, the following states, labeled as A12, are defined as shown in the diagram. The voltage changes during the normal charging process are illustrated in the second diagram. When not connected, is in state A. Upon insert the charging gun, it transitions to state B. After all detection points have correct money value in it enter state D and starts charging. In this study, a survey battery is utilized on the load side. Therefore, the charging voltage V01 is maintained at 15V, while the charging current I01 is controlled at 3A. The simulation result and depict in the following figure. The following image showcase the implementation result of the ACR with the master slave architecture. In the future, a scheduling algorithm will be incorporated into the server. The algorithm will optimize task allocation when multiple task requests arise, considering factors such as system capacity, user demand, device targets, and the time constraints in order to achieve an efficient task distribution outcome. This paper presents advancement is current charging equipment, argument, charging feasibility, and cost effectiveness for EVs. The proposed improvements, notably a novel max level framework, are geared towards optimizing the allocation of charging resource. However, challenge remains in attaining an ideal charging schedule and refine a system indicating the need for continuous development. Here are my references. Thank you.
Any question? No? Okay.
What charging protocol are you using?
I use the combined charging system (CCS), including CCS1 and CCS1 combo 1, CCS2 combo 2. As the main focus in my research, and this is currently the most mainstream globally.
Okay.
Can you explain what spatial advantage this method charging architecture has?
First and foremost, the primary advantage of master slave architecture lie in the occasion of charging resource. This design allows a single expensive charging robot to serve more people. Simply put, the mobile power supply characteristic of the master slave architecture eliminate the need to distinguish between charging parking space and regular parking space, thus avoiding the issue of occupying charging parking space.
Thank you.
Do you have any comparison result to verify your research?
我们像如果是以电，像刚刚前面有提到空气电压跟电流，那一个我们是有分其他比较。对，那个比较，因为我们是用电容模式控制，那电容模式控制它可能就是在它轮开时间比较快，然后像我们现在其实控那个也是控的蛮准的。对，那但是，那这个我们有呈现比较的部分。
Due to time limitation, we welcome the second speaker, Zhang Youqun. Okay.
Hello everyone, welcome to my presentation. I am a reporter. My name is Zhang Youqun. The title of my research is Improve IPID with fuzzy design on Crowdcaptor. And this is outline. First, I will introduce mathematical model, then say about several control methods and show simulation. In this In this case, we use a mathematical model of four axes and areopherical and U and V to control the attitude angle and altitude using model-free control MFC as a best and an intelligent PID control and adjust the observer parameters using fuzzy control. So there are two types of mathematical models for Procaptor. One for cross-type model and one for X-type model. The cross-type model is better for analysis, but the X-type model is better for actual flight control. So the X-type model is used as a control model. And the following is a mathematical representation of the four axis particle, which includes the position state and x, y, z, and the attitude state phi, theta, psi, and the attitude is the angle of rotation of the object around the coordinate system. U is the control signal, G is galactic parallel, I is moment insurer for XY axis, M is total weight of the protector. And PID control. PID control is widely used and has a advantage that the controller doesn't need to know the system model in advance and only needs to exploit the error between the measured value and the ideal value. And this is a model-free control. And model-free control, the model-free control is based on a mathematical model and can be online. And temperature direction, IPID is calculated by its input signal to eliminate to unknown part and combine with the general PID control to get a better control effect. And actual extended state value and the extended state observer error is a very important parameter for the whole control of state values of the extended state observer are relative to the extended state observer error, and right side and left side is the extended observer error state type, and right side is actual extended state value and extended state observer error. So the extended state observer is used to estimate the unknown part and external interference of the function f, which requires the systematic current, state value, and state observer value. taking the input values as the difference between the reference signal and the state and the state derivative of the difference between the reference signal and the state. This is by deciding that the input value are differentials of the difference between the reference signal and the state, the difference between the reference signal. And the state and I design their attribution functions. The input value are the triangulate attribute. And input 1 is the error between the ideal value and the state value of the system. Input 2 is the error between the ideal value differential and the state value differential of the system. And there are also different methods for defalsification. This is case using the center of gravity as to defalsify and obtain the output value. The center of the gravity value is obtained by calculation the fuzzy set B. And so this case use MCU ST32 F52352 with the center to achieve the control of the character. And MCTN is used to control the electronic governor, which can control the brushless DC motor. UART is used to receive and transmit the actual sensor, and USART is used to communicate with the mobile phone using Bluetooth to send commands or receive data. And the use of Bluetooth and cell phones to do communication in order to send commands or receive data. Used as a sensor measurement using ultrasonic sensors to measure the height. The resistance of the hardware still need to be adjusted, so there are still a lack of actual video, so just a simulation. So here use MATLAB to do the simulation. Yeah. The blue line is IPID and the red line is PID. And yellow line is reference symbol. Then use MATLAB simulation to compare with not using fuzzy control. And blue line is using fuzzy, and orange line is not using fuzzy control. Then in this case, modified extended state observer is designed on an intelligent reality control by adding a fuzzy control to the extended state observer. The oscillation of its attitude angle are reduced, which makes the performance of the file system better than the modified extended state observer. This is reference. Thank you for your attention.
Any question? Okay.
What are the advantages of using the S-axis model for quadcopter analysis?
Its computation makes it easier to maintain unverified, providing a stable platform, and it is strong maneuverable. Is maneuverable, yes, and allowing it to flexible response to change in direction.
Okay.
How does it play a role in adjusting the observer parameter in the UAV control system in fuzzy control?
By counting fuzzy control with an extended state observer, and a solution and each attitude angle can be reduced, and thereby improving the performance of the file system. Fuzzy control can help adjust the performance of the observer to better adapted to the ending of the system. Yeah. So in achieving more stable and precise control.
To the first page, your device is repeat what?
Yeah.
What?
Oh. Oh. Oh, sorry. Sorry.
Yeah. Who is it?
Sorry. No, sorry, this is mine.
So you work? No problem.
Sorry, 我马上改。
Any attention, we welcome the third speaker. Third speaker. 王胜。你们现在放吗？Okay. Okay, thank you.
Hi, my name is Xiaoru Wang. Today I will be presenting my paper on enhanced speed estimation based on 2D object detection and molecular vehicle pulse estimation. And this is my outline. I will talk about research motivation. First, let me introduce what ITS is. The full name of ITS is Intelligent Transportation System. It is the utilization of advanced electronics communication, computer control and sensing technologies in various transportation systems. Through real-time information transmission, it enhances safety, efficiency, and service, improving traffic issues. Furthermore, it is classified into 5 major functional systems. Among them, in the advanced traffic management system, the aim is to conduct traffic monitoring using various sensor technologies, with speed estimation being its core, directly impacting road safety and traffic management. Next, I will introduce the sensor commonly used in the past to locate traffic objects, as obtaining the actual position of traffic object is necessary to calculate their speed. Camera provide rich RGB information, but due to their sensitivity to lighting condition and lack of depth information, they cannot achieve high precision object positioning. Radar and LiDAR, on the other hand, can actually locate objects in adverse weather and environmental conditions, but the downside is their high cost. Based on the rich information and low cost of cameras, I believe that they have highly development potential. Therefore, I design and construct and apply deep learning that can effectively check object position information from image, thus improving the accuracy of estimating the movement speed of traffic object using image. In this paper, the authors utilize the method of 2D object detection for vehicle localization. Subsequently, they create a virtual detection box in the image to calculate the speed based on the time and distance when the vehicle passes through this box. And the authors of this paper use the same method for vehicle localization as the previous one, which is the 2D object detection model. However, they introduce a spatial approach by transforming the image into a bird's eye view using perspective transformation. They estimate the vehicle speed by calculating the displacement change of the vehicle in the bird's eye view. However, I pose a question and a challenge. Can the center point of the bounding box from an object detector truly represent the actual center point of a vehicle? I believe it might not be correct. In this sample, the blue point represents the center point estimate use the 2D detector, while the red point represents the true center of the vehicle. This example demonstrates that using 2D detection box for vehicle localization may not be meaningful, especially in complex scenes. It reminds us that in the process of vehicle localization, we need more meaningful and precise method to determine the center point of the vehicle in order to improve the accuracy of estimation. Therefore, I believe that if we find the center of the vehicle in the image space and map it to the bird's eye view space, not only can we more accurately locate the vehicle position. Sorry. Not only can we more accurately locate the vehicle position, but we can also remove the depth information problem, and to use this as the central idea of my research methodology. Next, I will describe the specific methodology. Initially, I employed a 2D object detector, YOLO, to detect the vehicle position in the image space. By cropping the image to remove the background and retain the vehicle instance image, I input it into the post-estimation model. The first step involved feeding the image into a fully convolution network, FCN, to regress the heat map. Subsequently, the positions of these key points are regressed from the heat map to the coordinates within the vehicle instance. Finally, applying transformation is applied to the image to obtain the position of the key point in the image space. On the other hand, to check vehicles and achieve the functionality of multi-vehicle speed estimation, I utilize a data associate method BITE. This method categorizes detection box into high score and low score box. The Kalman filter is then used to predict the position of the detection box in the next frame. A two-stage approach is implemented to associate detection box and the predict box, achieving multi-vehicle checking. In order to integrate visual information with geometric information to enhance our understanding of the environment, I begin by matching the checked vehicle ID information with the geometric information estimated from the post. Subsequently, building module fusion is performed using a perspective transforming method to map the post features. This maps the vehicle post center point to a shared representation space. But I will improving the accuracy of representing the vehicle position in the bird eye view space while maintaining the 2D post center coordinates. In speed estimation, I first calculate the vehicle displacement by including the position of the vehicle center post in the bird eye view for each frame. Using the Euclidean distance formula, I calculate the pixel displacement between nearby frames. Subsequently, I calculate the time per frame and distance transformation metric for each frame. The distance transformation metric is determined using the known dimensions in the bird eye view and actual miniature dimensions. Finally, utilizing the displacement between frames TPS and the distance transformation metric, I apply the speed formula to calculate the speed. However, even when the speed is calculated, a problem may arise. Even if the vehicle stays parked, there might still be slight change in posture between different frames. These changes are caused by variation in the surrounding scene and affect the calculation of the vehicle speed. In the scene, the vehicle is park stationary on the road, but their slight positional change is made in different frames. So I smooth out the initially calculated speed using sliding window to eliminate the influence of displacement association on the speed. I take the average of the speed of the current frame and the speed from the previous two frames. The resulting value is then revised and considered as the new speed for the current frame. I compare the result of the past method, which directly calculated vehicle speed in image space using 2D object detection, with the method I proposed. Both experiments were conducted on two identical vehicles in the same time and environment. The left image represents the past method, while the right image represents my method. From the experimental result, it's clear that the old method had huge errors when it comes to calculating the instantaneous speed compared to the actual speed of the vehicle. This is because in their speed estimation method, they were using average speed instead of instantaneous speed to assess performance. Once we switch to observing their performance using instantaneous speed, we unexpectedly found their shortcoming in this aspect. On the other hand, our method not only can more accurately and reasonably estimate vehicle speed within tiny time intervals, but it also significantly reduces speed association due to the use of sliding window. In this picture, the yellow line represents the estimated driving speed of vehicle in the image using my method, while the red line represents the actual speed of the vehicle collected using GPS. So we can find that my model has high accuracy in real world. This is my qualitative result, where I visualize the speed estimated by the model and draw key points as 3D box, which each side colors different. This is my conclusion. The experimental result demonstrate outstanding performance, improving position estimation, and reducing uncertainty. The regressions of object central is crucial for actually locating object position from image. Through our research, we successfully integrated 2D object detection, molecular vehicle cost estimation, and improved speed estimation algorithms, significantly enhancing vehicle positioning. We look forward to bring tangible benefits in traffic management and improvement of intelligent transportation system in the future. Thank you for your attention.
Any question? No? First of all, I have I would like to commend your presentation's quality is very good, and the slide is well prepared. Is it published? Is work
on the true from true.
I mean the publish is the conference.
Oh yes, yes.
Okay.
ICC.
ICC. So the presentation is based on the conference.
Yes.
Okay. I'm wondering, you said that you have good contribution. First of all, is the hardware. Can you go back to the conclusion?
Yes.
Okay. First is the integration of 2D object detection, molecular vehicle cost estimation.
Yes.
This is the hardware integration to enhance your performance. The next one is the speed estimation algorithm software. 这个也是你的那个提出的贡献。
Yes.
两个都有。
对。
I'm wondering, the simulation result page. 你刚刚那边有给了两个比较啊。对。这个或前面都可以。For example, this one, ID7 slash GT.
GT is structure，就是红色的线是代表这两个都是同一台车，那红色的线代表那个用 GPS 去进行真实数据的收集，那收集到的是真实车辆在路上行驶的移动速度，那黄色是用我的方法提出的测速，用影像测速的速度，对，那就是这个结果是来看说，跟实际上是有准确度是有在的。那如果是这边的话，左边的话是使用传统的方法，就是也是用 2D object detection 方法去做测速，但是它没有用多模态融合的方式让它映射在同一个共同特征表现，那它的测速上面就会有些不准确。那它以往在它论文上面是看起来是准确的，是因为它用的是频率速度的方法。那我的方法是可以在瞬时速度，对，那它的方法我拿来测在瞬时速度上面就会是非常的不准，因为瞬时速度是用 megapixel 的中心点去做测速的。对。
My question is, the difference between the existing work and your work include the hardware and the software, or only which part? 你的方法跟他的方法啊，比方说你刚硬体你有整合两样，这个单眼相机啊，还有那个 2D object 的这个 detection。那在软体上你又有这个速度侦测的演算法，也就是说这两个加起来是你这个 work 的这个整体的表现的这个来源嘛？
对。
那既有的 work，比方说它硬体是什么样子？它有那个吗？有单眼相机吗？
对，原本都是在单眼相机的。
OK，还有 2D object detection 这些。
对，就是它的方法，原本的方法跟我的方法都有包含 2D object detection。那所有作用在的场景都是单眼相机所拍摄到画面。
那你跟他猜这是在哪里？
就是等于说环境一样，那我跟他的差异是说，
你的演算法。
对，我演算法，他用的是 bounding box 的中心点去做速度，去做车辆的定位，那我是用车辆的关键点去做定位，就是我回归它的 key point。对。
你是那个余正老师？
不是，我的老师是那个许成建老师。
OK，因为你们毕业都很秀，我都不知道你们是谁。
忘记。
OK， 好了，OK。
How do you decide the sliding window size? Because there's 3, but
SX3。Yes，我的方法就是，比如说3帧，我把3帧的，因为有时候会有误差，那这个我要怎么去？因为误差是从哪里来？误差是从像左边这边，它会有震荡，那这些震荡是代表说它用 model 去预测出它每个车辆中间的时候，你就算车辆不动，但是你在这一帧跟下一帧的时候，有时候会因为模型的误差导致会有微小的震动，那微小震动在瞬时速度上面就会很明显会有震荡的反应。那我要怎么去抚平这些震荡呢？那我就是用 sliding 的方式，我用比如说0、1、2、3帧，那我就是取这3帧去做平均速度，当做第1帧或是第2帧都可以，就是当做那个当下的瞬时速度。那这样的结果就会造成，我每3个变成一个平均速度，去算它的瞬时速度，那就可以去抚平它这些震荡的问题。
Okay, we welcome the first speaker.
Hello everyone, I am Cha Yu Xie. My advisor is Professor Chin Yu Li. My subject is the Canada or intelligence and power rail SD Canada circuit. This is my outline. First, I will introduce my motivation, SD background, and traditional power rail SD Canada circuit. Then I will talk about my proposed circuit. I named it almost power rail SD Canada circuit. And is how to work during SD stress and normal stress. In addition, simulation and experimental results can verify the SD operation ability of my proposed circuit. From layout and chip photo, my circuits are read in TSMC 0.18 micrometer CMOS process. In failure analysis, we can find where are damage in SD tests. Finally, performance comparison can tell us the proposed circuit have a better performance than the general circuit and other circuit from reference. With the progress of progress, the size of device in IC is getting smaller. So IC are more easy to break down by ESPL, electrostatic static discharge. For most, ESD can easily cause damage to the gas side. Therefore, design a super ESD protection circuit to protect every internal circuit is necessary. Okay. For some applications, it may design or almost designs. In these applications, our ESD protection circuits also use almost without PMOS to design. Easy because we can reduce our mask of process. We can reduce our chip cost. Yeah. So some RF or high-speed IC, they may adopt ON type design because it almost have a higher actual mobility. So this design can be really employed. Okay. We can the figure show the two models. First is HBM, a human body model, and the second is machine model. The two models have a safe start standard to ensure the clarity of the products. HBM can simulate a human with that electric touch the IC. NN can simulate a machine touching IC in failure. CDN or charge device model is important now because in a advanced process, this model, this small ESD events can damage our IC. Because it is very fast, its discharge time is shorter than HBM and NAND. Conclusion: the ESD specification is 215 in CDN, and HBM and NAND is 2000 volt and 200 volt. This system, this future show system, we call it a TLV system, transmission line Hertz. This system can generate a high voltage and transient Hertz to zamp our device. So it can measure IP curve during the Hertz and the leakage after zamping. So the two index is important. First is trigger voltage, we name is VD1, and second is second breakdown current, we name is ID2. First index can symbol our ESD connection circuit speed, and second index can symbol our ESD robustness. Yeah. So we can use the two index to observe our port circuits have a good performance. This structure is a whole chip ESD connection circuit structure because ESD made occurs on the pins of IC. We can find the structure have a VDD and IOP and BSS. So we should set a ESD connection circuit in between power supply and IOP. We can have two modes, discharge phase, PS mode and ND mode. So a power resistive circuit is important for this structure. It stays between VDD and VSS. So my research focus on power resistive campus circuit. This is a traditional power resistive campus circuit. We can find we have a RC electrical circuit and an inverter and a discharge device. We name is NESD. In this circuit, during ESD stress, the RC circuit, the connector, we can do it short to front. So in ESD event, inverter can offer a high voltage to NSD to treat it to turn on. Yeah, NSD turn on to discharge NSD current. And normal work, RC will offer a high voltage to inverter, and inverter is over low VG on VG. So NSD will close during normal stress. This is my proposed circuit. I name is almost power efficient circuit. We can find it is only using MOS without PMOS. I use extra RC differential circuit to control NN1. So it can replace MP, and this MP PMOS. So this design can only use the MOS. This circuit, during ESD stress, it can N1 is open and N2 is closed. So VG is high, so NSD can turn on to discharge ESD current. Okay, we can find this circuit have two current meter circuit. This use current meter can amplify our resistance, so it can reduce our chip cost and layout area. Use for MOS to replace the resistor. We can find traditionally have a poly resistor. but this use a MOS. It's because use police will have a large layout area. So use a MOS to prevent police visitor can reduce our layout area. This is simulation result. We can I use an SD-like cursor is 5 volt to on the power rail. We can find the whole circuit have a lower VG. This because current mirror circuit have a special voltage to cause the circuit trigger lower. Yeah. So this cause our SD current. The right figure show the SD current in simulation. But in fact, in experimental result, the whole circuit have a higher SD reference. It's because lower VG can scatter our SD current from most channel to P substrate. This is leakage simulation. We can find our two circuits have a similar leakage and various process corners. Yeah. And this is leakage simulation result and different temperatures. We can find in 25 degrees, it has about 6 nanoamperes. And 100 degrees, it has only a very small discrepancy. This is my layout and chip photo. We have a 30 test key to investigate the pathogen. Okay. And this chapter produced 1 year ago. This is experimental equipment. The figure shows the measurement of the HBM and EC tester. The tester can send our device with HBM standards. We can change the black box to hit center HBM or center NN. This is TLP system. The system has 3 equipment. Power supply and oscilloscope and TLP. And TLP can 0 Hz to Z our device, and oscilloscope can record voltage and current waveforms during Hertz. And power supply can measure leakage after damping. So this is an experimental result. We can find NN-ESD label. We can find the whole circuit with 600 micrometer width. It has 64 volts in NN-ESD label, and traditional circuit only has 600 volts. So we can verify our whole circuit has a higher SD performance than traditional circuit. This TLP tester result. We can find our circuit, the whole circuit have a higher IDQ than traditional circuit, but the trigger voltage is higher, so my whole circuit is lowly triggered. But the breakdown voltage of internal circuit is about 10 volts, so this circuit can protect our IC. Yeah. This is a very fast TLP. A very fast TLP is simulated CDN SD event. So this tester is we can find it have a similar result. The proposed circuit IDQ is higher than traditional. VT1 is also higher than traditional circuit. This is leakage tester result. We can find the two circuits have a similar leakage, and 25 degrees the whole circuit have about 5 microampere and traditional have 4 microampere. And other degrees, we have a similar leakage. In order to verify the circuit can protect our internal circuit, we use a MOSFET to check our circuit can protect it. So if monitor not breaking, so it have a low leakage. If we break down, we have a higher leakage. At least our experimental result, we can find 2 circuits. We have almost monitor or not, or no almost monitor. We have a similar IT2 in TOP and with very good TOP result. NSD level, they have a similar result. So we can verify our circuits have a good ability to predict our IC. This is a failure analysis. We can, to the 2 figures, find damage region in NSD and other. Yeah. So we can adjust our size of NSD to increase our SD robustness. Okay, this is my performance comparison. We can find my proposed circuit have a higher IT2 and complete layout area. It is important for we only use a MOS to design. And we have a higher version of the TLB IT2 to area. Yeah, so my proposal is have a very great performance in this comparison. Yeah. Okay. Like conclusion, all ATM circuits be realized in TSMC 0.18 microsiemens per process. From experimental result, it is verified in its EAT protection abilities in the HBA and CPA events. The layout area of the proposed circuit is smaller than traditional circuit. The leakage, the 2 circuits is similar. So my proposed circuit is great. It's a great urge to reduce the chip cost in operation our internal circuit of IC. Yeah. Okay. Thank you for listening.
Question?
Could you please explain the importance of CDM for ESD protection? Like, which situation does it simulate for?
CDM is important because it is very fast. The charging time is very short, about 5 milliseconds. So in advanced process like FinFET or GAA process, this CDM event will be very dangerous. So now we are focused on this mode. So we have a very creative test to verify this mode, this easy event. Okay.
Okay, thank you.
Why traditional circuit needs an inverter to trigger?
Okay.
Why traditional circuit needs an inverter to trigger?
Okay. use inverter is reduce the layout area because if I directly use RNC to trigger NC, this have a very large layout area. Because RC contester is about 1 microsecond. If I have inverters to trigger, RC contester only have a 0.1 microsecond, so it can reduce our trigger cost. Yeah.
Thank you.
Yeah.
It seems like a very good approach and a stand-down winner than the traditional method. But has there any cost or other drawback?
它有没有其他不好的地方？对啊，它完全都已经看起来不传统的方法，它都没有任何那个。你说我对你的方法跟传统方法，然后什么地方要稍微再那个要这样讲。
原则上来说，我的电路它的问题会在于它的 process 的 variation 会比较大一点点。可是我们可以从那个模拟结果看到，其实就是 SS 的 corner 它的影响是比较大的。这个问题是有被克服，虽然它确实是有影响没错。那除此之外的话，其实目前还没有想到什么会输传统，当然跟其他网页比可能还是有优缺点，可是跟传统比应该是全胜。
那如果说从那个它的那个 cost 或者是制成的一些，比方说成本啊，
复杂度的话，虽然我们的设计复杂度是比较高的，可是我们其实在制造成本上，它可以少掉，因为我们是只用 NMOS 而已，所以我们可以省掉一层让它长跟为了那层光照，所以它成本比较低，而且我们可以从这张表发现我们的 error 其实是最低的，对，所以它的成本理论上应该是最小的。
Okay, the next one.
，Good morning, everyone. My name is Chen Xiao, and my advisor is Professor Lin Xunyong. And my research topic is knowledge parallel ESP cancer with double detection mechanism. This is outline part. First, let me begin by explaining some general information on electrostatic discharge. I will then introduce parallel ESP cancer. In this experience, the robustness and reliability of circuit are explored through various steps. Finally, the conclusion and future work will be introduced. First, the electrostatic discharge is ESP may generate several amperes of current in 10 to 100 nanoseconds, causing damage to IC if they don't design any ESP protection method. So ESP protection has become a major concern on the reliability of IC products. To sustain good ESP robustness, the parallel ESP can circuit plays an important role in ESP protection design. And leakage current not only leads to unnecessary power consumption, but can also affect the operation and reliability of the device. Next, I'll introduce the component level ESP test. Human body models simulate the situation when electrostatic charge accumulates on the human body. When touched and IC, the electrostatic charge from the body is transferred to the IC pin and then discharged to the ground through the IC. This discharge process occurs in a span as short as a few hundred nanoseconds, generate a momentary discharge current of several amperes, capable of destroying components within the IC. During IC manipulation, it is also possible for electricity discharge to accumulate inside it. When this IC happens to be grounded, the amount accumulated in E will form an ESD current and be discharged to the ground, which is a CDM event. The discharge time in this model is even shorter, only within a few nanoseconds, and the discharge phenomenon is more difficult to accurately simulate. As important as component level ESD, system level ESD refers to the ESD event that from systems are exposed to during daily use. In order to ensure that end user can use the electric product normally and safely, manufacturers should conduct system level ESD testing on their product with the IEC 61000-4-2 spec. This is called a human echo model. When designing the ESD protection device, must lay the working area of device between the maximum supply voltage and the device breakdown voltage. In the normal work condition, the trigger voltage VT1 must be lower than the breakdown voltage. Otherwise, the internal circuit will fail by ESD current before the protection device has turned on. The holding voltage VH must be higher than the maximum supply voltage. Otherwise, the protection device will produce a large number of leakage and it will cause the main circuit distortion. Additionally, the turn-on resistance on of the protection circuit will determine the power loss on ESD event. Finally, the ESD robotics or protection device can use the secondary breakdown curve IT2 to determine the ESD protection device is good or not. Next slide is parallel ESD CAN circuit. The RC-based parallel ESD CAN circuit uses an inverter to drive and turn on the ESD. Under normal power conditions, the RC trigger circuit is unable to turn on the ESD. With the flex power condition, the rise time of VDD voltage may be fast enough to cause a mistriggering on ESD. The image on the right shows the voltage at the NESD gate rising, leading to a false triggering of the NESD. When this mistriggering event occurs, the NESD with bigger device dimension will cause a large leakage. To overcome the false trigger issue, the downstream is the typical circuit used to detect the overstressed voltage level. This is down trigger parallel ESD CAN circuit. The difference from the RC-based circuit is that it utilizes voltage detection. During the ESD event, the voltage of VDD can turn on the downstream. On the other hand, it won't turn on during normal operation. Due to the base power condition, the voltage isn't high enough. We just let the voltage rise quickly, so it won't turn on. However, during normal operation, if NOS cause the voltage to rise, it could also potentially cause false triggering. And use the downstream often suffer a leakage issue because the parasitic diameter and its current amplification within the downstream under high temperature. Therefore, the double detection mechanism circuit was designed to avoid the issue mentioned earlier. When an ESD device occurs, MP1 and MP2 are turned on to conduct a voltage into the node VG to trigger on the NESD. And during normal power condition, the NESD won't be triggered. And during the fast power, MP1 is turned on, MP2 is turned on. So the NESD won't be activated. For normal work condition, a control circuit has been added to reduce the voltage across the downstream and reducing the leakage current. This circuit and P4 turn on only during normal work condition. At this time, the voltage across the downstream will be very low. This table is about the parameter of the proposed circuit. MESD was designed in three sides to investigate the impact of different sides on the discharge capability. Then the various conditions of the circuit were simulated by using HSPACE. The first simulation was for an ESP event. All nodes behave as expected, with the MESD gate voltage VG reaching 4.3 volt, successfully triggering the MESD to discharge current, and VRV voltage 3.2 volt is approximately the same as the turn-on voltage of downstream. Next, the simulation is under normal power condition. The MESD gate voltage remains at 0 volt. Finally, the base power condition. The MESD gate voltage remains at a low level. According to the simulation result, it can prevent fault triggering during base power. This is the experimental visualization. The proposed parallel ESP10 circuit is fabricated in a 0.18 micrometer with 1.8 volt CMOS process. The tape out date is May 29, and chip out date is September 21. This is the chip micrograph for the proposed circuit. The PLP system can generate a single high-energy pulse wave, making an effective tool for simulating ESP event on the chip. During testing with PLP, the intensity will be gradually increased until the test circuit shows a normal leakage current under normal power condition, indicating failure. After the mission, IV curve can be obtained. Through this data, we can observe VT1, VH, IT2, and leakage current. To characterize the CDN robustness of ESP voltage circuit, use very fast PLC system to verify their performance. To investigate the turn-on behavior of the parallel ESP10 circuit under the base power condition, using PLC to create a waveform with low voltage and narrow scale rise time. According to the experimental result, the proposed circuit can immediately fault triggering during base power on. The HBM ESP robustness of the proposed circuit has been tested. In this test, the failure criterion is defined as 30% increase from the original leakage under 1.8 volt VDD bias. To measure the leakage current, a semiconductor characterization system is used to measure the leakage current under 1.8 volt VDD bias. At room temperature, the leakage current is only 1.97 microampere. After heating to 125 degrees Celsius, the leakage current is only 110.2 microampere. Then use the ESP gun to obtain HMM robustness. The ESP gun that compared with ICE 61000-4-2 standard generate the system level ESP. This will use contact discharge, which discharge and ESP pulse direct from the ESP gun touching the DUT. From the measurement result, it can be seen that the proposed circuit has reached a certain level of IT2 and HBM robustness. In terms of leakage current, Additional control circuit to reduce the voltage across the downstream can effectively reduce the leakage current. According to the performance comparison table, the circuit produced this time has the best performance in reducing leakage current. This is the conclusion part. The proposed circuit is fabricated in a 0.1 micrometer CMOS process. Double detection provides immunity against false trigger event, and the leakage current achieves a very low speed. The final section is about future work. HMM robustness is insufficient. So with the common required in 8,000 volt, future work will